Hello friends, in the previous few lectures we have been considering the assumptions that we make to arrive at the schematic representation of the mechanical behavior offered by metals and alloys. Now an elegant way of representing it, or a straightforward way of describing the mechanical behavior that is exhibited by metals and alloys, involves a graphical representation that includes both the condition that we impose and the response offered by the material. Now, the assumption that we make while presenting the mechanical behavior offered by the metals and alloys in this schematic representation is, we assume that the metal is exposed to uniaxial tensile loading and the response offered by it is exclusively associated with change in the length or change in the longitudinal dimension of the material. So these assumptions help us arrive at a schematic representation that captures the mechanical behavior offered by the metals and alloys. One is the uniaxial tensile loading and the other is the exclusive consideration of the change in the longitudinal dimension offered by the material. Now, in the previous lecture, we were able to relax both these assumptions. Now, our consideration or our discussion on Poisson's effect, it helped us include the lateral strain or the change in the dimension of the material in a direction perpendicular to the loading direction. So when we consider uniaxial tensile loading, the loading direction is along this arrows. Now correspondingly, the longitudinal change in the dimension is parallel to it. So the exclusive strain that we have been considering for the stress strain curve or the load elongation curve is always has been along the loading direction. The response that we have been considering has always been along the loading direction. Now the inclusion or our discussion on the Poisson's effect, it helps us accommodate the strain or the response along the direction that is perpendicular to the loading direction. So if x is the loading direction, through the consideration or discussion of the Poisson's effect, we were able to accommodate the strain along the perpendicular direction. Now in our previous lecture, in addition to considering this the strain along the lateral direction, this additional strain that is observed just for the uniaxial loading condition, we were also able to relax this assumption of uniaxial tensile loading and extend it to biaxial tensile loading. So the Poisson's effect, it allowed us to discuss the strain in the direction that is perpendicular to the loading direction. And in the previous lecture, we extended our consideration to biaxial tensile loading in the sense that when we impose the mechanical condition, it has tensile loading along two directions, both along the x and y axis. So we have stress sigma x and sigma y, that is stress along both x and y direction, and we were able to arrive at the response offered by a material, expression for the response offered by the material for under biaxial tensile loading. Now the response offered by the material under biaxial tensile loading we categorized into direct and indirect response, and the direct response was along the loading direction and the indirect response was in the direction perpendicular to the imposed load. Now in order to appropriately describe or appropriately represent this direct and indirect response offered by the material, we considered parameters that involved two subscripts. So the strain, it is usually the response offered by the material. When we are discussing in terms of strain, it is represented by epsilon. And in order to distinguish the direct response from that of the indirect response, in order to encompass all the different forms of responses that is offered during or that is exhibited during the biaxial tensile loading, we considered an epsilon or a parameter, this representation that included two subscripts. The first subscript, it indicated the strain direction, the direction along which we observe the response, and the second subscript, it indicated the loading direction. When the strain and the loading direction are the same, then what we observe is a direct response. When the loading and the strain directions are the same, so that is when the response that you observe is along the loading direction, then what we have is a direct response. When the subscripts are not the same, when they are dissimilar, what we observe is an indirect response. Now the indirect response is principally caused by the Poisson's effect, and the indirect response is along the direction that is perpendicular to the loading direction. So in case of biaxial tensile loading, we have a convoluted response that is offered by the material. In order to capture this convoluted response, we need to have a parameter with two subscripts, so epsilon with two subscripts. This helps us distinguish direct response from that of the indirect response. So ultimately what we end up having is, in case of biaxial tensile loading, we have two direct responses and two indirect responses, and we were able to arrive at an expression for the overall response in a given direction. So overall response in a given direction. So when you have just one subscript, it is the overall response or the overall strain in this case x direction or along the x axis. So when we do that, the expression they arrived at is of this form: epsilon x is equal to 1 by E. So this nu here is the Poisson's ratio. So this is the expression that we arrived at, or we derived in our previous lecture, that under biaxial tensile loading, the overall strain in a particular direction comprises of two components. It is introduced by two stresses along the x-axis and also the stresses along the y-axis. That is, under the biaxial tensile loading condition, both the stresses that we impose, both the load that we impose along the perpendicular direction, both contribute to the strain in a particular direction. So we introduce under biaxial tensile loading stresses along x and y direction. Both these contribute to the response that we observe in a given direction. So in this case, the given direction is x. We want to see the overall strain that is along the x direction. The overall strain on the x direction is a response that is offered by the material for both the loading condition. It is not governed by only one loading direction, but it is governed by, it is dictated by the loads along both the direction, that is along the x-axis and also along the y-axis. The similar expression we were able to derive for the overall strain along the y direction. So what we have essentially considered is a material which is exposed to biaxial tensile loading, and the response we observe, irrespective of the direction we consider, is, if we can consider along the x-axis or along the y-axis, irrespective of it, is the combination of both the stresses that we impose on the system. It is not uniquely governed by a single stress, but it is the combination of both these stresses. Now, let us expand or extend that assumptions that we have considered so far. That is, we have been restricting ourselves, or we have been largely focusing on biaxial tensile loading thus far. Now let us extend this assumption and consider triaxial tensile loading condition. So how the triaxial tensile loading would look like for the sample that we have been considering thus far is something like this. So we have the longitudinal direction. So if, for the sake of triaxial tensile loading, let us consider a frame of reference of this sort. So we have our x-axis, we have our y-axis, now we have our additional axis, that is the z-axis. So the stress along the x-axis is in this direction. The load that we impose along the x-axis is in this direction for our sample that we have here, and the stress along the y-axis can be represented as this. And finally, we have the new stress that we impose. It is towards the screen that you are viewing, so it is along the z-axis. So maybe a better representation. Yeah. So it is along the z-axis. So this is the new stress that we impose, and since we have stresses being imposed, tensile stresses that are being imposed on all the three directions, what we have on three directions, we have we refer to it as the triaxial tensile loading condition. Now we want to arrive at the similar response expressions that we have for the biaxial loading condition. So we have for the biaxial loading condition the response that is offered by the material along a specific direction. So let us see what would be the response offered by the material in a given direction when we expose the material to the triaxial tensile loading. So discussion that proceeded for the biaxial loading condition will be extended to the triaxial loading condition. Now before going into the actual derivation, let us see what are the different responses that a material offers for a biaxial, or rather in a triaxial loading condition. So let us see what are the different types of responses that the given sample offers when we have or when we impose a triaxial tensile loading. Of course, the overall response that a material offers to a complex loading conditions such as this can be categorized as the direct and the indirect responses, like we have considered for the biaxial loading condition. And the direct response, the characterizing feature of the direct response is the response direction or the strain direction. Strain or the response direction offered by the material is parallel to the loading direction. In the same way, or it's the contrary what we observe in the indirect case. In case of indirect strain, the response that we observe is perpendicular to the loading direction. So since in case of the direct response, the strain direction and the loading direction are the same, we subscript the epsilon assumes, we subscript the parameter assumes is identical. And in case of the indirect response, since the loading direction and the strain that we observe are perpendicular to each other, the subscripts, the parameter assumes are different. So in case of biaxial tensile loading, that is what we observed, we will adapt the same representation approach. So we will have epsilon that comprises of two subscripts, and in case of direct loading, since the response direction is parallel to the loading direction, the subscripts will be of the same notation. So therefore epsilon xx will represent one direct response, and epsilon yy will represent another direct response. And finally, since we also have a load along a stress along the z direction, we will have an additional strain along the direct or additional direct strain along the z axis. Now when you consider the, so this is the representation for the direct response that we observe when we impose a triaxial loading condition. Now the indirect response, this indirect response stems from the Poisson's effect. That is, when you impose a load in a particular direction, there is a response that is offered not only along the loading direction but also in the direction perpendicular to it. So therefore the indirect response, particularly in this context, can be represented by the notation that involves two different subscripts. So when you consider this notation here, we have already seen the first term indicates the strain direction, the response direction. The second term indicates the loading direction. Now when you consider the strain that we observe along the x-axis, in addition to this strain being brought about by the corresponding load, this strain along the x-axis can be also brought about by the strain along the y-axis, or rather the stress along the y-axis and also the stress along the z-axis. Now when you consider a response along a specific direction, there are two ways that this response can be brought about. So if let us for instance focus on the x direction alone, if we focus on the x direction alone, the strain that we observe in the x direction can be brought about in two ways. One, it could be along the loading direction, so through this load we will be able to observe a response. Or on the other hand, because of the Poisson's effect, there will be load that are active on the perpendicular direction, and that load will bring about a strain in this x direction. That is what we observe here. So we have loads that are acting, the stresses that are acting along the y and the z axis, and due to the Poisson's effect we have a corresponding strain along the x axis. So that is what we mean by indirect response, and we have captured it here. So along the x-axis, the strain that we observe is brought about by the load along the x-axis, the load along the y-axis, and the load along the z-axis. Along the x and z-axis, that is the perpendicular axis, the perpendicular direction, these loads bring about a strain along the x-axis due to the Poisson's effect, and that is what we have represented here. So similar to the strain along the x-axis, we will have strain along the y-axis that is brought about by the load along the x-axis through Poisson effects, and the load along the z-axis again through Poisson's effect. And the same way, we will have response along the z-axis that is brought about by the stress along the x-axis and the stress along the y-axis. So what we essentially end up having is, under triaxial tensile loading, there are 3 direct strain and 6 indirect strains that we observe. So we are imposing, we have extended our assumption to biaxial to triaxial tensile loading, and when we do that, we observe that there are 3 direct responses and 6 indirect responses. Now, based on the notation, we will be able to rather describe this overall complex form of the strain that we observe during triaxial tensile loading in a form of a matrix. This overall strain that we observe during a triaxial tensile loading can be expressed in a matrix notation. So we will have, represent it in this manner, wherein along a given row you fix the strain direction. So in this row, what you observe is the strain that you see along the x direction, and in this row we will include the strain that we see along the y direction, and in the final row we will include the strain that we observe along the z direction. So what we have done is, the entire strain, the convoluted strain that we observe, the convoluted response that we observe when you impose a triaxial tensile loading condition, we have represented it in the form of a matrix. So maybe down the lane, or if you take a course, or out of your own interest, if you want to understand even further on the elastic behavior of materials from a mathematical perspective, this is often referred to as a tensorial notation, and here we have narrowed, or we have arrived at this representation by considering the response offered by the material. We have taken simple or rather a straightforward approach to arrive at this representation, but the same representation, when you take a purely numerical perspective, you will be able to understand this can be arrived at, or a given strain, a given response for a complex loading condition can be expressed directly in this manner of matrix representation, which is also called as tensorial representation. So what we have in this case done is, we have considered a triaxial loading condition, and from that we were able to arrive at this form of representation. But when you take a numerical perspective, when you take a mathematical perspective, you will find that we can start from this matrix, and then we will be able to reduce the overall strain that is exhibited by the material for any given loading condition. So in our case, started off with the triaxial loading condition, ended up with this representation, this matrix representation, or this tensorial representation here. When you take a complex approach, or when you take a purely numerical perspective, you will find that it will be easy for us to start from this and then express the overall strain the material exhibits based on its loading condition. So if you consider a simplistic loading condition, then certain terms will assume the value of 0, and then the matrix will be a simpler, straightforward matrix. So this is just to give you some thoughts on how complex your representation of strain will become as you increase the loading condition, or when you take a numerical perspective, how from a complex looking representation of the strain, you will be able to narrow it down to a simplistic case. So when you start from this, like I said, when you start from this representation of the strain, now that you know how we have arrived at it, and now when you start from this representation of the strain, by substituting appropriate values to each of these entities here, based on the loading condition that you impose. Supposing there is no load along the z-axis, then all these terms wherein the second subscript is z will become 0. So therefore, what you are doing is, depending on the mechanical condition that you impose, we will be able to express the overall response that is offered by the material using this notation here. So it is possible for us also to start from this notation. Now that we have understood how we are able to arrive at this representation, we can start from this and use this to depict or represent any form of the response of a material for an imposed loading condition. This is just a side thought. Now, what we essentially have achieved is, we have represented the direct and the indirect response that is offered by the material under triaxial loading condition. We are moving away from biaxial. We have started with uniaxial, moved to biaxial, now to triaxial. The triaxial now has helped us present the strain in a comprehensive manner, and depending on the loading condition, we can reduce this comprehensive representation of strain to fit our loading condition. So appropriately fit our desired condition that we observe. Now, let us arrive at an expression for each, or we will try to arrive at an expression for both the direct and the indirect strain that we observe under triaxial loading. Now, when you consider the direct responses, for example, now that the z direction is the one that we have recently included in our discussion, so let us consider, or let us focus on this direction alone. So for the z direction or z direction, the response that we observe, particularly the direct response that we observe, is of this form, epsilon zz. Now, for this direct response is dictated by the stress along this particular direction. So this strain is a direct response that acts along the loading direction, and the load that we impose, the stress that causes this particular strain, is along the z direction. Now, assuming that the proportionality constant that relates the stress to strain is same in all the direction. So when we assume that the proportionality constant or the Young's modulus that relate stress to strain is same in all the direction, x, y and z, again this is what we refer to as the isotropic material or isotropic behavior. When we assume that, then in that case the relation between the stress along the z direction can be expressed as the product of the Young's modulus and the corresponding direct response. Now again, all this is possible because we are focusing on the elastic behavior. We have exclusively focusing on the elastic behavior of the material, so therefore we are directly able to relate the stress along a specific direction to that of the strain that is also along the same direction. Now we have an expression for the strain, the direct strain along a specific direction, which can be written as the load along the same direction by the corresponding or the Young's modulus. So the same expression is adapted by all the direct responses. It means the direct response along the x-axis will be the ratio of the stress along the x-axis to that of the Young's modulus, and the strain along the direct response along the y-axis will be the stress along the y-axis to that of the Young's modulus. So we have now three different expressions for, we have specific way of representing the direct responses that we observe. So we have arrived at the expressions for the direct responses. Now let us try to arrive at an expression for the indirect response along the z-axis. So the indirect response along the z-axis will be of this form. So this here, the term here epsilon zx, what it represents is, we have a strain along the z-axis that is introduced by, or that is brought about by, the stress along the x-axis. So we are imposing a stress along the x-axis, and due to the Poisson's effect there is a strain along the z-axis, that is the perpendicular direction. So since this response is brought about by the Poisson's effect, we can use the Poisson's ratio to describe this particular strain. So the Poisson's ratio is, so assuming that we are considering isotropic material and sustaining that assumption, so the Poisson's ratio along the x-axis is equal to the one along the y-axis and also along the z-axis, so it's a constant. Now the Poisson's ratio for the load that is imposed along the x direction and that brings a strain along the z direction is the ratio of the lateral strain, that is zx, and the longitudinal strain or the strain along the loading direction. So therefore epsilon xx. So what we end up having is we have considered the Poisson's ratio and we have considered the strains along the perpendicular direction. So one along the z direction and one along the loading direction. So therefore we have arrived at an expression such as this. Now the response that we are interested in is epsilon zx, and that is nothing but minus of the product of nu, that is the Poisson's ratio, and the direct response along the x direction. Now we have an expression for epsilon xx, that is here. So we have an expression for epsilon xx which we have derived here. So therefore the indirect response along the z direction that is brought about by the load along the x-axis is represented by minus nu. So this term here, we are substituting this term here. So sigma x, that is the load along the stress along the x direction, and the Young's modulus. So what essentially we have done is we have now arrived at an expression for the indirect response or the strain along the z-axis that is brought about by the load along the x-axis. Now in the same way, another indirect response, that is the strain along the z-axis that is brought about by the stress along the y-axis, can be expressed as minus nu, the stress along the y-axis, and our Young's modulus. Again, we have not added any subscripts to either the Poisson's ratio or the Young's modulus because we have assumed our system to be isotropic. Now what we have essentially done is we have arrived at we have considered the indirect responses along the z-axis and we were able to arrive at the corresponding expression. In the same way, it is also possible for us to express the indirect responses along the x-axis. So it will be of the similar form. So therefore it will be the product of the Poisson's ratio, the stress along the y-axis, and the Young's modulus. The same way, the indirect strain that is brought about along the x-axis due to the stress along the z-axis will be the product of the Poisson's effect or the Poisson's ratio, the stress along the z-axis which we have considered here, stress along the z-axis, but the ratio with respect to the Young's modulus. Now we have the indirect response along the x-axis and here we have the indirect response along the z-axis. So indirect response along the x-axis and here the indirect response along the z-axis. Now what is left is the indirect response along the x-axis, and it can be represented as epsilon along the, or rather indirect response along the y-axis, so it can be represented as epsilon y, and this response is brought about due to the load along the x-axis, and therefore the expression is of the form like this. And in the same way, there is also a response along the y-axis that is brought about by the loading direction z. So this is represented in this manner. So we have here three expressions for each of the direct responses. So we have three direct responses and we have expression for all the three, and we have also found that there are 6 indirect responses and we have derived the expression for all the 6. Now this is how we have represented the overall response, and as you can see, the diagonal entities, they indicate the direct responses, and the non-diagonal elements, they indicate the indirect responses brought about by or which is induced by the Poisson's effect. And for all the 9 different components of the stresses, we were able to arrive at a corresponding description, a corresponding formulation. Now let us try to find out for or under triaxial loading. Under triaxial loading, what is the total strain that we observe along the x-axis? So we want to know under triaxial loading what is the total strain that we observe along the x-axis. So this is the total strain that we observe, that we want to quantify along the x-axis. So this is the summation of the strain, the direct strain or the direct response along the x-axis, and the indirect response along the x-axis. So triaxial tensile loading, we want to quantify the overall strain along the x-axis. So it is the combination of the direct response and also the indirect response. The overall strain, combination of direct and the indirect response. Now we have an expression for the direct response, that is epsilon xx, and that is sigma x by E. And we also have an expression for epsilon xy, that is indirect response epsilon xy. So we have an expression for this here, and therefore we can correspondingly substitute the terms. So it's minus mu sigma y by E. In the same way, we also have derived the expression for epsilon xz, the response that is brought about in the x direction because of the loading along the z direction. So that we have here, and we can substitute the similar terms, that is minus mu sigma z by E. Now it is possible for us, so we can just manipulate this expression here, take the common terms out, and if you do that, we can take the 1 by E out, and if you do that, we end up with an expression of this sort. So the overall strain along the x-axis for triaxial loading condition is of this form here. What we have is the overall strain along the x-axis for the triaxial loading condition. So we have, characteristically for triaxial loading condition, we have 3 different stresses that brings about the overall strain. Now for a given direction, all these 3 different stresses contribute to the response. So for a given direction, the response can be direct and indirect. When you combine all these 3 stress, all these 3 load that we impose on the system, it gives the response, and that is the expression we have here. So even though we are considering the strain along a specific direction, all the 3 components of the stresses, all these 3 stresses that we impose on the system, it offers or it contributes to the overall strain that we observe. The overall strain is the product or is the function of all these 3 stresses that we impose. All the 3 stresses that we impose, it governs the overall strain in a given direction. Now all the other strains, the strains along the other different direction, will be of the same format. We can use the same approach to derive the strains along the other directions as well. So therefore the overall strain along the y direction will be of this form, like this. So it will be of the similar form, only the stress, the role played by the stresses will vary. So here the direct stress assumes the first term, and the indirect stresses, the stresses that brings about the indirect responses, they assume the position of the second and third term. So that is the form of this expression here. The form of the description for a strain along a specific direction under triaxial tensile loading is the stress that brings about the direct response assumes the first term, and the other stresses that introduces indirect effect assumes these 2 term here. So in case of the strain along the y direction, the stress that brings about this strain is the stress along the same direction, that is sigma y. So it assumes the first term, and all the rest of the stresses assumes the other terms. So in the same way, we will be able to express the strain, the overall strain along the z direction. So it will be of this form here. So I hope I have captured the notations properly, but the form of the expression remains the same. The stress that brings about the response along the respective direction is assumes the first part here, and the rest that brings about the indirect response are these 2 stresses. So what we have done is we have achieved an expression for the strain along the x-axis, the strain along the y-axis, the overall strain along the y-axis, and the overall strain along the z-axis for a triaxial. So these are overall strain under triaxial tensile loading. So under triaxial tensile loading, we are now in a position to describe the response in specific direction. Now, what essentially we have so far been considering is, we have been considering different forms of loading condition. We began with uniaxial and then we moved to biaxial. So we began with a simplistic case like this, a uniaxial tensile loading, and we moved to a biaxial tensile loading. So in addition to the load in this direction, we also consider load in the perpendicular direction. So this is uniaxial and this here is biaxial, and now in this lecture we have considered a triaxial tensile loading. So the load along the longitudinal direction, the load along one of its perpendicular direction, and we have also considered the load pointing towards us. So we have considered different forms of loading. So despite this consideration of the different forms of loading, the way we have considered the response has always been oriented towards the specific direction. So even though we have been increasing the complexity of the mechanical condition that we impose, the response that we observe, we have so far been describing it based on a specific direction. So we have been describing the response offered by the material either based on the x-axis as here, or either based on the y-axis as here, and either based on the z-axis as here. So what we have not done is, we have not cumulatively expressed, we have not considered or collectively expressed all the overall response that is offered by the system as a whole. So we have a system, we have a sample, and when we talked about the response offered by the material for the complex loading condition, we described it based on the direction. We oriented ourselves towards a specific direction, and we said when we consider the strain, when you consider this direction, this is the response that you observe. When you consider this direction, this is the response that you observe, and when you consider the other direction, this is the response that you observe. And all these directions are the loading directions. When you consider this particular loading direction for the triaxial loading, so this is the response that you observe. When you consider a y-axis, y loading direction, this is the response that you observe, and along the z-axis, this is the response that you observe. So even though we have been increasing the complexity of the loading condition that we impose, we have thus far been representing the response that is offered by the material in a same manner. So the manner in which we have represented the response has not changed. So when we want to render a comprehensive, a complete description of the response offered by the material in a holistic manner, not just along a specific direction, but how the overall sample changes or responds to the loading condition, then in that case we need to consider the overall or change in the overall volume of the sample. A generalized way of describing it is system. Now when we want to get rid of, or when we want to have a generalized description, a description that is not restricted to the directions as we have right now. So we have considered biaxial loading, we have considered uniaxial, and we have also considered triaxial. Irrespective of the loading condition, the way we represented it, we represented the response, it involved a specific orientation associated with it. On the way we described, or we arrived at this expression, all these expressions are valid only for a specific direction. Now when we want to comprehensively describe the change or the response offered by the material in a holistic manner as the sample as a whole, then what we need to consider is the change or the change in the overall volume, the total, the entire volume of the sample. How the entire volume of the sample changes for a given loading condition will give us an understanding of how the overall effect will be perceived by us when we impose a given loading. So impose, so when you consider, or when you rather do this particular or impose this particular loading condition in a laboratory setup, and when you observe a certain change in the dimensions of the sample, it is rather difficult for us to perceive or align ourselves to see what is the change in the dimension along in that direction. But by looking at the sample, the way the sample has changed its dimension, it will be easy for us to perceive how the entirety of the sample has changed, how the overall sample has changed. Now this overall sample, what a parameter that helps us describe the overall change in the dimension of the sample is the volume. So what essentially we will be doing in the next lecture is we will be trying to address the volumetric response that is offered by the material in a loading under a loading condition. Instead of considering the response along the specific direction, we want to see what is the volumetric response, the entire volume, how it changes for a given loading condition. And when you have such an when you have such a volumetric change, how well it can be expressed. So that is what we will be looking into the subsequent lecture. So instead of representing the response based on or exclusively associated with a specific direction, what we will be doing is we will be considering the sample as a whole, the whole entire volume of the sample, and then we will try to arrive at an expression for how the volume of the sample or the entire volume of the sample changes for a given loading direction. Now what we will be doing is we will not be starting with the uniaxial tensile loading, but we will be starting with the triaxial tensile loading. From now on, since we have already been exposed to the triaxial tensile loading, we will be starting with the convoluted representation of things, and then from that we will be able to narrow it down to our specific condition, like we saw in our representation for the overall strain. In this case, it is possible for us to start with this representation for a strain and then manipulate it based on the loading condition that we impose. In the same way, we will consider the change in the volume of the material, the change in the volume of the sample for triaxial tensile loading, and then we will arrive at an expression, and then we will see how this generalized expression for triaxial tensile loading can be reduced to address both biaxial and uniaxial tensile loading. We will arrive at a generalized expression for the change in the entire volume of the system under triaxial tensile loading, and then from that we will narrow it down to biaxial and uniaxial. So this is what we will be looking into in the next lecture. See you then. Bye.